Welcome everyone. My name is Kostas Arvanitis. I'm a senior lecturer in museology at the University of Manchester at the Institute for Cultural Practices, and I'll be chairing this event. And this event is organized jointly by two of the research platforms of the university, which I will come to in a moment. Just a reminder that this event is being recorded, and the recordings of the presentations will be available online after the event. We will also record the discussion, but the discussion won't be on the website. So welcome again to this event titled AI and the Arts, Languages and Linguistics, which is, as I mentioned, organized by two of the university's research platforms. So I'll just share my screen very quickly to give you an overview of what we will be talking about. Digital Futures is one of the university's research platforms, brings together 1,700, well, about 1,700 researchers from different disciplines from across the university, across the three faculties of the university, into multidisciplinary communities to explore and address key research problems, build critical mass, and kind of address and work with external stakeholders on research projects and research problems that sit in the intersection of digital technologies and various disciplines, as outlined in this diagram that you see on the screen, covering from health and care to cities, employment, industry, citizens and democracy, creative and heritage, and institutional challenges. And these are the kind of the vertical kind of subject areas, where the horizontal themes, the horizontal kind of lines refer to cross-cutting capabilities that cut across different disciplines and different themes. The other platform, that research platform of the university that organizes this event, is Creative Manchester, which is one of the, I think it's probably the newest research platform of the university, started in October 2021, and facilitates interdisciplinary links between university-wide research programs, establishing new communities of researchers whose work utilizes creative methods and practices. Creative Manchester has three main research themes, which are creative industries and innovation, creativity, health and well-being, creative and civic futures. You can find more about both of these platforms, and indeed the other universities of Manchester research platforms on the University of Manchester's website, if you're interested in doing that. Right, so today's event is part of, it's a second of a series to explore and showcase the work that the university does on the intersection of artificial intelligence and the arts, cultures, languages, and linguistics at the university. Back in December 2021, we held our first event, which showcased work under two main themes, the ones that you see on the screen, on hybrid human-machine and immersive creativity and performance, with a particular emphasis on electroacoustic music, and using AI to enhance research and access to collections, audiences, and cultural heritage, with contributions to on museum research and the work that the John Rylands Library does around AI on enhancing access to its collections. On the Spark page link that we have on the screen, and I think that will be also be added on the chat in a moment. you can find a recording of the relevant presentations. So that was the event back in December. So today, what we'd like to do is to highlight some of the research that colleagues at the university do on AI and the broader kind of data science and computational methods in languages and linguistics. And to do that, we have two speakers. Today, Dr. Adrianini, who is a lecturer in English language, will talk about computational authorship identification. And following Andrea, Dr. Colin Barnard, senior lecturer in linguistics, we will present his work on using computational linguistics to detect markers of Parkinson's disease in typing data. We had a third speaker today, Dr. Ricardo Bermudez Otero, who was going to present a voter model approach to the distribution and dynamics of typological features of language. But due to unforeseen circumstances, Ricardo, sorry, I had to cancel his participation today, but we will make sure that we invite him back to a future event. So the structure of the event will be as follows. Andrea and Colin will present their work for about 10 or 15 minutes each. And then that I will open it up for questions and kind of broader discussion on the use and application of AI in languages and linguistics. If you like to make any notes or kind of note your questions in advance, please use the chat to do that, but we can also take questions at the end of the presentations as well. And I think that's all from me. I'll stop sharing my screen. And I will hand over to Andrea. Over to you.
Right, thanks, Kostas. I'll just share my slides just a moment. Okay. Right, so so what I will be talking about is the kind of work that I do in authorship identification using computational methods, and what I will argue is that quite controversially, I would say that I don't do AI, but also I would hopefully by the end of the presentation you understand how for the kinds of things that I do, AI is quite problematic and ethically challenging as well. But let me just first begin with an introduction, just for those of you that are not familiar with these technical terms here. So if we think about linguistics as the scientific study of how language works, and you can have different overlaps with various disciplines, then linguistics can be done theoretically to understand how language works, or it can be used to solve real-world problems, right? And examples of applied problems can be clinical, education, or forensic. And this is where I'm located, so the forensic applications of linguistics. And linguistics can be applied for forensic problems, for example, to understand the legal language, okay? But that's an area that I don't personally do. What I do instead is I apply linguistics in cases in which language becomes part of the evidence. For example, let's say that there is a disputed text and there are potentially two candidates. So say a threatening letter and there are two suspects that could have written it, and there are writing samples that have been collected from the suspects. Then what we can do is we can present the likelihood that one of the suspects was the author of this text, okay, which is a task called authorship attribution. Similarly, if there are actually the vast majority of situations is when you have only one suspect, and this kind of scenario is called verification, authorship verification. And finally, there are cases in which you have only one malicious or question text and no suspect at all, and these are cases of profiling. So all of this kind of work is called authorship analysis, and what I be mostly focusing on today is this subset over here, which is authorship identification. Now, before I go there, though, I would like to just show you a few examples, just two examples really of work on profiling, which is also relevant to the kind of things that I do and the kind of methods that are computationally driven. One example is the Sony hack case. So when Sony was hacked, I can't remember when exactly, but when this movie was released, the interview showing these journalists pretending to be journalists and actually being on a mission to the leader of North Korea. So there were claims that it was the North Koreans that hacked Sony to block the release of this movie. And so, in this case, you've got these hackers. So what you see here, this is a text that was sent by these hackers. And so the question that we can answer using linguistics is, to what extent can we derive characteristics about this person who wrote this text, right? Person or group of people. And the way you do that is you analyze. So there were like a number of letters here. Those are the sizes in terms of number of words for each letter. And what you can do a linguistic analysis of these letters, right? So for example, you can immediately notice that there are things that combination of words that don't really go together, which we call collocations. So these collocations are not standard. Other things like the non-standard use of prepositions, or the articles like the or a or n that were missing or not used in a standard way. And from knowledge that we have about this kind of behavior, then you can infer that these are not perhaps just not likely to be native speakers of the main varieties of English, like British or American English. But there are also things that are a bit more complicated that you find in these letters, where you need some computational help. So, for example, this kind of feature here, which I'm not going to explain in too much detail because it's not important anyway. We continue until your request be met. So that kind of be over there, which is clearly not standard English. So the question is, where do we find that? And it's a question you can answer if you have data, right? So for example, and we do have data. So we have data that comes from these corpora. Corpus is just a collection of texts. So we've got a corpus of learners of English, and more specifically for this case, corpus of Asian learners of English. That was relevant. So you've got about 4.3 million words, and then you can very basic data science here is who uses that. It's quite, I mean, the complex part is to identify the feature, but once you manage to do that, then you can look at the distribution and you can say, okay, right, so it looks like several languages in East Asia do have that. Now you can take that this kind of method a bit further, And for example, these kinds of problems happen to be common in the dark web, where crimes tend to happen, and it is normally quite difficult to identify people on the dark web. But through the language that offenders use, as shown before, we can use this information to identify them. So if we take that kind of method that I just showed you to its further, so we can just imagine this is a map of a particular expletive you see here, that the frequency with which this word is used in the United States, and it's proportional. So the red areas are where it's more frequently used than the rest. So of course, this particular expletive is used all over across the United States. So this is a matter of frequency. And we can do that with alternatives, for example. Like, for example, here we've got gosh, it's kind of the opposite. And then if we do that for multiple other words that are found in this particular text, we can then stack them on together and find a sort of area that narrows down the origin of the particular speaker. So now what you've seen here, this was actually used in a real case, and it helped profile the dialect region of an offender. Right, so AI, I wouldn't call this AI though. I would just call this statistics or computational methods, but it goes by, sometimes it is called AI. So I suppose that's, it is relevant to this, to the kind of conversation we're having here. But, so as I said, let me just spend a few more minutes, just a couple more minutes, to discuss more specifically identification. So what I showed you was profiling, right? So that how you do that for profiling. For identification, so when you have a suspect, then it's a bit different because you have comparison data. And what tends to be done in those cases is, so the kind of technique that is used is that you take, let's say we have this text, for example, here, I just toy text. What it's typically done is you break it down into words, the so-called bag of words. So essentially a text becomes like a bag of marbles, right? So you just look at the probability of extracting a word, of observing a word. But what is done in authorship identification is that not all the words are used. Only those words that are called function words are used. So, so these are things like the articles or prepositions, and these are things that do not contain information about meaning. They only contain information about grammar. And so once you have a data set of these kinds of words, then essentially you use statistical techniques to separate different authors in terms of their usage. For example, you can create a map like this, which is a multidimensional scaling done over a distance matrix. And you can, usually when you have enough data, and the data that is constrained in a particular way, so as long as you meet certain conditions, then you can distinguish authors in a reliable way. Now, the problem, though, of these methods, and that's what that's what I mentioned at the beginning of my talk, is that at the moment, this kind of work is done in a way that it's still relatively explainable. So that a linguist could say, okay, we say that this group of texts belong to the same author because we observe this particular function words, right, that are used in a way that is consistent. However, there are various other methods that are used by computer scientists where this kind of explainability is absent, because you can achieve very similar results, if not better results, if you use, if you look at, for example, just the frequency of letters, right? And this is something that the statistic, so there is a statistical signal in this text that is picked up by particular algorithms that will actually classify text according to their authors correctly, but that it's not essentially a black box. So we don't know what it's really doing, right? And this is an issue for forensic work, because if and when linguists are called to testify, they cannot, it's the linguist that is called, it's not the computer, right? So if the linguist cannot explain what's going on, and if the computer cannot be called to testify, then we have a problem, because that's not forensic science anymore, in a way. Okay, so I'll end this here, and I'm happy to discuss some of these issues during the Q&A.
Excellent. Thank you very much, Andrea. You've already given us a lot to think and talk about later in the discussion about the ethics and applicability of these methods and approaches. But we'll talk more about that after Colin's presentation. So, Colin, over to you.
Okay, I'm just going to share my screen and present my slides. Can you see that? Good. Okay, so hello, my name is Colin Bannard. I am also, like Andrea, in the Department of Linguistics and English Language. However, I work in a slightly different area of linguistics from Andrea, which I could position on his same hierarchy, as a lot of it falls under the applied wing. So I'm both a computational linguist, so my PhD was in computational linguistics, so that's concerned with area of linguistics concerned with processing, understanding, and generation of human languages by computers. So I started off my career working on machine translation. But then since my PhD, I've focused more on psycholinguistics. So that's trying to understand the mental processes that underlie human language. Now, what I want to talk about today is that it falls between those two fields. So this is using computational linguistics to understand the mental processes that underlie language. So, and lots of the same issues that Andrea raised are actually going to come up in my talk, which is nice. And essentially, there are lots of different ways you can apply computational linguistics in psycholinguistics. The way I'm going to talk about doing it today is essentially as a data analysis tool. So really, the reason I'm talking about using AI methods. So when I talk about computational linguistics, that's a subfield of linguistics, but also a subfield of AI. So the reason I'm talking about using AI methods, the way in which AI methods are being used here is as an analysis tool. And essentially, it's I use it when conventional statistical models don't really don't give me what I want. So so you think about language. So the primary way in which standard statistical models don't necessarily handle language very well is that language is something that happens across time, where there are different statistical relationships between words or between sounds. So you can't treat those words or sounds as independent events, and you also can't, and also that the relationships between them are structured in complicated hierarchical ways, and so that's really that's when AI models come in useful. So the specific task I'm going to talk about today is address it. So I work on applying AI to different aspects of psycholinguistics. So a lot of my work is on child language acquisition. So the work I'm talking about today is fairly atypical, I guess, in terms of my own work, but I think I chose to talk about it because I think it demonstrates the sort of basic principles I want to talk about best. So I'm going to talk about detecting Parkinson's disease in typing data. So Parkinson's disease is a neurodegenerative disease that occurs, affects nearly 1% of people over the age of 60. Its main signs include slowness of movement, tremor, and rigidity. So in order to motivate what I'm talking about, I need to introduce a little bit of biology. So the symptoms of Parkinson's disease, the motor symptoms of Parkinson's disease, I'm talking about slowness of movement, tremor, and rigidity, are caused by the degeneration of dopaminergic neurons in the midbrain. So this is depicted on the right here, with a slice of the midbrain of a person with Parkinson's disease at the bottom here, and without Parkinson's disease at the top there. So you can see that in the person without Parkinson's, there are these clear black markings here in an area that's called the substantia nigra, and these are absent in the people so the absence in people with Parkinson's disease. So I'm telling you about this neurodegeneration for two reasons. The first is that I think it's useful in understanding why the work here described in this talk is important. So by the time that the main signs of Parkinson's disease are apparent, over 50% of neurons in the substantia nigra, so here, have been lost. So this is later than we would like for any kind of neuroprotective intervention. So there's thus an urgent need for detecting neurodegeneration earlier. And ideally, the methods we use would be cheap and easy to collect. And so behavioral methods are ideal. And one kind of behavior that we have lots, we can easily collect data on is language. So the goal of the work here, described here, is to identify signs of Parkinson's disease in a behavior we all perform regularly, namely typing. The second reason I've talked about neurodegeneration in the midbrain, in talking about Parkinson's here, is that there's a particular pattern to it. And this can help us identify the kinds of behaviors, the kind of linguistic behaviors that might be affected in the very early stages. So human movement is controlled by multiple loops between different areas of the cortex and the basal ganglia, encompassing the midbrain. So different loops are responsible for different components of actions, ranging from automatically deployed habits to fully goal-directed behaviors. And language behaviors also span that range. So some aspects of language are automatic and habitual, and some are goal-directed, even consciously decided about. And the neurodegeneration in Parkinson's follows a particular course, beginning in areas of the basal ganglia that are involved in the sensory motor loop. So here depicted in blue, which is implicated in the production of habits and automatic behaviors. So as a result, it's been proposed that a very early sign of Parkinson's disease might be problems in the deployment of automatic behaviors. So in language, that'd be automatic aspects of language use. And that's why we're looking at typing. So typing is a heavily automatized behavior involving the sequencing of habitual routines, by which I mean the typing of keystrokes that have been produced many times before. Thus, we might expect to see very early effects of Parkinson's disease on typing. Now, we're not the first people to look at typing in Parkinson's disease. In fact, the related behavior of finger tapping has long been used in the detection and monitoring of PD. So in finger tapping tests, the participant is asked to alternately tap in two locations for a set duration. And this task is often performed on a keyboard, as is shown in the video at the top of the slide. So the finger is just moving between two keys. Now, finger tapping data is simple to collect and useful, but it suffers from the problem that general slowing is not specific to Parkinson's disease, and thus finger tapping cannot reliably distinguish Parkinson's disease from other disorders that involve slowness of movement. Now, in recent times, statistics from typing have been used in place of tapping statistics, based on the observation that people with Parkinson's disease will type more slowly. But again, these measures, that aspect of typing, the use of that aspect of typing suffers from the same lack of specificity as finger tapping. So it could be, slowing could be due to a range of different disorders. So recent work has begun to focus on the finer details of the timing of keystrokes, which holds the promise of greater specificity. However, all of this work has ignored information that we would expect to be important, and namely that's the identity of the key that is being pressed. So that's the linguistic information. It's focused purely on how long it takes to type particular keys or move between particular keys without being concerned about what the identity of those keys are. So the goal of this work was to develop a new model for identifying markers of Parkinson's disease that we thought would hold the promise of greater specificity to the disease. Wanted to test whether, specifically whether consideration of what is being typed, so the words that are actually being typed, can make a difference. So the question really is, can an AI model using key identity information and timing information perform better than a model including timing information alone? And then the other goal is to be able to examine what properties of the key press sequences our model picks up on. So this comes back to the issue that Andrea talked about of interpretability. So we can apply an AI, a complex AI model, but then the next question is, can we actually interpret? Can we learn anything from it? And I'm going to argue that we can. So in the published paper on this topic, we looked at 3 different data sets. So these all included participants copy typing sentences using the interface you can see at the top right of the slide. So they would be presented with a sentence, and they would be asked to type what they see. Now, 2 of these data sets were collected in clinics in the UK and Spain. So we had where the clinician identified people with Parkinson's disease within 5 years of diagnosis, and then we had a group of age-matched controls. Now, these tested in clinic data sets are obviously give us a great deal more control. However, essentially, I think the success of this kind of data collection, and one of the attractions of this data collection, is that it's easy to collect and doesn't require people going into clinics. So we also looked at online collected data. So this is 100 people with Parkinson's disease within 5 years of diagnosis and 130 age-matched controls, each of whom copy typed 15 sentences. So when I talk about the analysis in this data and the results in the remainder of this talk, this is the data set that I'm talking about here. So keylog typing data gives us quite detailed information about the movements involved in typing. So in the lower part of the slide here, you can see a representation of the time period between the pressing of 2 consecutive keys. So there are 3 separate and potentially valuable measures we can take from this. One is the time taken from one key press until the next key press. So this is the inter-key interval. The next is the time between the pressing and its release. So this here is the hold time. And the third is the time pause between the release of the current key and the pressing of the next, which is labeled here as the pause. Now, each of these potentially reveal different information about the cognitive processes, motor processes involved in the pressing of this key and the surrounding keys. At the top of the slide, you can see the information that is presented to our AI model. So it's passed a series of characters that are being typed. So here the participant is typing pronunciation. And it's also passed, each of which is paired with 3 different timing statistics. So the inter-key interval, the hold time, and the pause. And so this is the fundamental data that we're looking to analyze here. Now, we could analyze this using traditional statistical methods. So for example, we could use standard time series models. The problem with that is that we would have to pre-specify exactly what kinds of relationships we were interested in. So we'd have to, we'd be able to tell it which we were interested in, the statistical dependency between how long they took to type the key A and what type and what key they were pressing 2 characters previously, for example. The advantage of using AI models is that we don't have to pre-specify. The model can discover this, and that's part of the power of machine learning. So the model works as follows. So the information is passed into a convolutional layer. So this is essentially a way of extracting the features from this set of characters and timings that we're interested in. So we're looking to essentially generate informative features by looking at local key press and timing interactions. In our network, this is then passed through to a recurrent neural network, which then outputs, which essentially gives us compresses down the sequence of the whole sentence down to a single representation. And then this is passed to a classifier, which then tells us whether the sentence being typed was typed by a person with Parkinson's disease or by a control. So there's one further thing that's important to note before we move to looking at the results. This is that a transformation was applied to the timing information. So as I said before, typists differ in terms of their overall typing speed. And overall typing speed is a useful indicator of disease status. However, we want to pick up on a different and more specific, more Parkinson's disease specific features. So therefore removed between participant overall differences in timing by scaling. So these are, each of these in this plot here, each of the lines represents an individual participant's timing, and we change all the times so that each participant's data is centered around 0 and has a similar spread. So the information that we're passing to the model then is not differences, but overall differences between participants, but rather differences in how participants type particular sequences. And if we're looking for trying to look at the pressing of specific keys, that's very important. So I'm going to spend that long on this, but the results, basically what we do is classification is performed at the sentence and the participant levels. So we're trying to either classify an individual sentence as whether that's been typed by a person with participants, or we're taking the full set of 15 sentences and saying, were these sentences typed by a person with Parkinson's or not. So what we did was compare models with timing information only and models with timing and character information. So essentially we're looking at whether adding in information about the identity of words, so the linguistic information, is actually having an impact. And what we found was including the character typed in our models improved a critical statistic here called area under the curve for all data sets relative to a time-only model. So we find is that with between participant differences in the overall average and spread of key presses removed, even with that removed, our AA model is able to distinguish patients from controls based on how they type particular character sequences. Our final goal is to interpret. So we use a method developed in the AI literature for actually the machine vision literature used to understand and interpret convolutional neural networks, called GradCam. And we use this to derive scores indicating the extent to which each key press contributes to the classification of that sentence as being typed by a person with Parkinson's disease. So you can see at the bottom here, we have this example participant has typed the sequence different pronunciation. This funny character here is a delete key. So they first of all type E and then they make an error and go back. And then we have the key press information for each of these keys. We also have other additional timing information. And the color of these keys here tells us how important that key is in identifying identifying whether the typist had Parkinson's or not. So the keys that are blue were not very important, and keys that differ from blue up this scale here were more important in that. So we can then look at the distribution of these scores and look at what our network is picking up on. So we can identify two key signatures of Parkinson's disease. So one is that people with Parkinson's disease show slowing for key transitions that occur within a hand. So for example, where both keys are typed by the left hand rather than where they're switching from one hand to the other. And the time intervals between the keys and healthy controls are greater for low frequency character sequence combinations, where this pattern is dampened or absent in people with Parkinson's disease. So we can think of this as a signature of habit. Essentially, people without Parkinson's disease speed up when they're typing things that they frequently type, whereas in people with Parkinson's disease, this is gone. And can be interpreted as being evidence for the depletion of the habit network that I talked about. Okay, so I see I'm slightly overrun here. So I guess I'll just skip to my higher level summary, which is that I think that AI models can give insight into linguistic behaviors that aren't possible using standard statistical models. However, as Andrea raised, interpretability is key. So the development of methods for interpreting models is essential to this. And I looked at in this particular work one way in which interpretation could be performed. And I think there are lots of developments in the field of explainable AI that mean there's more and more interpretability. Thank you very much.
That's great. Thank you very much, Colin, for that.